In this video, we will discuss the iterative solutions to linear equations, systems of linear equations. Recall that the standard form of a linear system in n unknowns is given by this form below. So you have here a11x1 plus a12x2 plus a13x3 and so on up to a1 and xn equals b sub 1 and so on. So yung ating systems of equations, para kasi magkaroon tayo ng isang unique solution, kailangan meron tayong n equations and n unknowns, no? Kasi meron tayong possibility na magkaroon ng infinitely many solutions. So if you can recall from linear algebra, na kapag meron tayong lesser number of equations sa system natin, tapos meron kang mas maraming unknowns, most of the time, nagiging infinite yung solution mo. And we don't want that. Kasi kapag infinite yung solutions natin, ang nagiging sagot natin ay in terms of a parameter. At hindi natin gusto na ganun. Kasi sa numerical methods, gusto natin, ang kailangan natin or ang nakukuha natin ay exact numerical value. Correct? So, ibig sabihin, ang mga systems natin na tinitingnan dito kapag sinosolve natin numerically ay mga systems na may unique solution. Alright? Kaya we have n by n na system. N equations and unknown. So, ang iterative solutions natin include these two, Jacobi method and Gauss Seidel method. So, the Jacobi method is pertain to as iteration by total step, while Gauss Seidel method is known as being iteration by single step. So, what is the difference between the two, total step and single step? Makita natin mamaya sa example. So, before you proceed with the iteration using either Jacobi method or Gauss Seidel method, you have to first check for what you call a convergence criterion. So, the convergence criterion, which is specifically called the row sum criterion, ensures convergence, okay, to the values of the actual solution. No? So, kasi kapag yung system natin, although unique, okay, let's say, you have a unique solution, no, to the system, and then, ginamitan mo siya ng direct methods, no? Let's say, Kramer's rule ka, or elimination substitution ka, no? Or inverse method, whatever method you used, makukuha mo yung value ng solution, no? Okay? Exactly, no? Kung ano man yung actual na value or analytical solution niya. Pero sa numerical methods kasi, kahit na yung system mo may unique solution talaga, kasi ginamitan mo ng numerical methods, Jacobi or Gauss Seidel method, posible na hindi mo pa rin makuha yung actual value kung hindi siya nagsasatisfy or hindi mo makuha, hindi ka makakuha ng approximate value kung hindi mo masatisfy yung criterion natin. Dahil instead na magko-converge siya, magde-diverge ang makukuha natin ng mga values, no? So, you have to satisfy the criterion, no, such that in a row, okay, the absolute value of a sub ii is greater than or equal to the summation from I equals 1 to n, where I is not equal to j, of the absolute value of a sub ij. Going back to our system, okay, general form of the system, yung mga a sub mn, so a sub 1, 1, 1, 2, 1, 3, a sub 1n, and so on, are numerical coefficients. Okay? Now, the a sub ii are actually those that are in the main diagonal. Okay? A sub 1, 1, 2, 2, 3, 3, 4, 4, up to a sub nn. Right? So, bawat isang row, merong a sub ii siya. Sa row 1, a sub 1, 1. Sa row 2, a sub 2, 2. And so on and so forth. Now, ang a sub ij are other elements, okay, doon sa row na yon. Okay, so a sub ij, a sub 1, 2, 1, 3, 1, 4, and so on and so forth. No? So, dito, sa first row, okay, ang a sub ij mo is 1, 2, 1, 3, 1, 4, up to 1n. Sa row 2, a sub ij mo is 2, 1, 2, 3, 2, 4, and so on. Sa third row, ang a sub ij mo ay a31, a32, a34, and so on and so forth. So again, ang sinasabi ng row sum criterion, sa isang row, yung absolute value ng element sa main diagonal, which is this one, will always be or should always be greater than or equal to the summation of the absolute values of all the other elements on the same row. Okay? So, yun lang. No? So, kapag na-satisfy yun sa row mo, ibig sabihin, lahat ng rows dapat. So, sa lahat ng rows satisfy, then it means na ensured yung convergence natin. So, sigurado tayo na when we apply the numerical technique, makakuha tayo ng converging values. Otherwise, magda-diverge yung values na makukuha natin kahit na alam natin na meron siyang exact or unique value. Okay? So, kailangan yung row sum criterion masatisfy sa lahat ng rows. Kung sa halimbawa, 3 rows yon dahil 3 equations meron tayo, sa first row, second row, na-satisfy yung criterion, pero sa third row, hindi pa rin siya ensured na magko-converge. So, kailangan buong lahat ng rows natin will be diagonally dominant. So, yun yung tawag sa system, okay? Kapag na-satisfy nga yung row sum criterion, the system is said to be diagonally dominant. Okay? So, kung hindi siya diagonally dominant, ang pwede natin gawin is to rearrange the equations in the system. Okay? So, actually, meron pa tayong ibang way kung paano mababago no, yung kapag hindi diagonally dominant yung system natin, kung paano siya ma-modify. Pero sa case natin, ang titignan natin ay yung mga kayang ma-modify using or by just rearranging the given system. So, after natin ma-ensure na na-satisfy yung row sum criterion, what we do now is to transform algebraically the given equations. No? Transform the diagonally dominant system to solve for one unknown in each equation in terms of the other unknowns. Okay? So, anong ibig sabihin nun? So, for example, let's say ito na yung ating diagonally dominant na system, no, na rearrange na natin. Halimbawa, tapos ito na yung lumabas na final form ng system natin, final arrangement. So, itong 3 equations na to, so ibig sabihin, 3 unknowns din meron tayo. x1, x2, x1, x2, x3, halimbawa. Okay? And so on. So, depende kung ilang unknowns ang meron doon sa equation mo. No? Sa halimbawa, up to x3 lang tayo. Kasi lang naman ang pinakamaraming posibleng ibigay, no? In our case. So, let's say, tanggalin na natin tong Okay. So, a1, 3x3 equals b sub 1. This one is so let's say meron lang tayong 3 equations, tas 3 yung unknowns natin, x1, x2, x3. So, ano ibig sabihin ng transform algebraically and solve for one unknown in terms of the other? So, dito, sa unang equation natin, we solve for x sub 1, our first unknown. So, x sub 1 will be equal to, so, syempre, transpose natin, okay, so, b1, tas na-transpose mo yung a1, 2, x2, at saka a1, 3, x3. And then, to solve for x1, kailangan natin i-divide both sides by a11. Tama? So, that will be, read ko lang to. That will be 1 over a11 times this quantity. Okay? And then, dun sa second equation, ang isosolve mo naman doon, yung second na unknown, which is the x2. So, x2 is equal to, so, b2, and then minus, transpose mo si a21 times x1, transpose mo so minus a23 times x3, and then divide by a22. And then, dun sa third equation, you solve for x3 naman. That will be b3 minus a31 x1 minus a32 x2, and then divide all terms by a33, or that's 1 over a33, multiplied by 1 over a33. Ito ngayon yung magsisilbi natin na iterative formula. Okay? So, yan yung gagamitin natin pang solve ng refined estimates natin ng x1, x2, at x3. So, nagbabago-bago na lang, depende kung Jacobi method or Gauss Seidel method ang gagamitin mo, kung paano mo ipa-plug in, okay, yung values dyan. Now, note na, kung hindi given yung initial guess natin ng x1, x2, x3, ang ginagamit natin ay 0, 0, 0, okay, bilang initial guess. Again, pwede tayong bigyan ng kahit na gaano karami equations and with given n equations and unknowns, pero sa atin, no, ililimit lang natin tayo sa 3 hanggang 3 unknowns, no. So, pwedeng 2 and then hanggang 3 unknowns lang. So ito lang yung pinaka maraming equations na ating i-handle, no. Alright, so let's have an example. Find the solution of the system. So given you have 3 equations with 3 unknowns, we use Jacobi and Gauss Seidel. So magkahiwalay ito, no? So basically, we will be doing 2 separate solutions, no? Up to a relative error of less than or equal to 10%. So we will first check if the system, given system, is diagonally dominant. Using our row sum criterion. So for row 1, titingnan natin, dapat yung absolute value ni 2, yung numerical coefficient A11, should be greater than or equal to the absolute value of negative 1, yung numerical coefficient ni x2, plus absolute value of negative 7. So is 2 greater than or equal to 1 plus 7? So that's false. 2 is not greater than 8. For the second row, absolute value of, so row 2, absolute value, ano ba yung nasa diagonal sa row 2? Yung negative 2. Okay? Ito yung nasa main diagonal, yan yung A22, negative 2. Is it greater than or equal to 5 plus 3? So is 2 greater than or equal to 5 plus 3? So again, this is false because 2 is not greater than 8. And then for row 3, so ang A33 natin ay 1. So absolute value of 1, is it greater than or equal to absolute value of negative 3 plus absolute value of 9? Okay, so this is 1 greater than or equal to 3 plus 9, which is again false because 1 is not greater than 12. So hindi niya satisfy yung row sum criterion. So ang gagawin natin ngayon is we will rearrange. Okay? So we rearrange the system. Pag ni-rearrange natin yung system natin, ang pagpapalit-palitin mo lang yung location nung equations, kung sino yung first, second, and third. Hindi po pwedeng pagpalit-palitin yung terms within an equation, or lalo na hindi pwedeng yung isang term sa isang equation dagay mo sa isang term sa another equation. So that's not valid, no? So ang pwede lang gawin, kung ano yung ayos initially, no? Okay, natin, ito yung equation 1, halimbawa, equation 1, equation 2, equation 3. Yan yung pagkakasunod-sunod initially. So, yan yung pwede mong bagu-baguhin lang nung ayos. Kung sino yung nauna na equation, pangalawa equation, pangatlong equation. Okay? Yung terms hindi pwedeng babaguhin yung ayos. At kung ano man yung pagkakaayos ng unknowns, x1, x2, x3, pare-parehas din dapat ng pagkakaayos, okay, sa lahat ng equations. So dito, gagawin mo lang is dapat yung pinakamalaking value nandun matatagpuan sa main diagonal. So ibig sabihin, kung titignan natin yung original equation natin, no, yung 5 dito sa second row, okay, kung siya yung nasa main diagonal, okay sana kasi ang kasama lang niya 2 and 3 eh. Okay, so magiging greater than siya sa 2 plus, greater than or equal to, okay, 2 plus 3. So pwede mo siyang iakyat para mapunta siya sa row 1, no, yung 5x1, para mapunta doon sa diagonal natin, iaakyat mo siya, gagawin mo siyang first equation, para yung 5, yung A11. And then, ganoon din dito, yung 9, nasa gitna siya. Mas mataas siya dun sa 3 plus 1 eh. Kaso, hindi siya yung nasa diagonal. Eh, since nasa gitna siya, pwede mo siyang iakyat papunta sa second, as second equation. Okay? And then, yung first equation originally, dahil yung 7, yung pinakamataas sa kanya dito, at nasa dulo siya, yung 7 na yun, pwedeng mapunta sa diagonal kung nandun siya sa pangatlong pwesto. Okay? Dun sa ating system. Okay? So, yung rearrangement natin, okay, ang ifo-follow na niya ngayon na ayos will be 5x1 minus 2x2 plus 3x3 equals negative 1, negative 3x1 plus 9x2 plus x3 is equal to 2, and 2x1 minus x2 minus 7x3 is equal to 3. So, yan yung magiging arrangement natin. At pag chinek natin ngayon, okay, sa row 1, absolute value of 5, okay, is now greater than or equal to absolute value of negative 2 plus absolute value of 3. So, 5, this one gives 5 greater than or equal to 5. So, this is correct. Sa row 2, ito yung ating A22, absolute value of 9 greater than or equal to absolute value of negative 3 plus absolute value of positive 1, which translates to 9 greater than or equal to 4, which is again true. And then sa row 3, ito yung ating A33, absolute value of negative 7 greater than or equal to absolute value of 2 plus absolute value of negative 1, which translates to 7 greater than or equal to 3, which again is true. So, lahat ng row nag-satisfy na ng row sum criterion. So, ibig sabihin, yung system natin is already diagonally dominant. Okay? System is diagonally dominant already. So, ang susundin natin na form ng ating system na, arrangement ng system natin, ito nang bago ha. So, yung original na system natin, yung arrangement, wala na tayo doon pakialam. Okay? So, yung iterative formula natin na gagamitin or gagamitin natin for our iterations, manggagaling na dito sa arrangement na to. Okay? So, magkaiba kasi, di ba, ang iterative formula natin nanggagaling yung x1, we will solve x1 sa first equation, x2 sa second, x3 sa third equation. Kung titingnan mo sa original na arrangement natin na given, iba yung iterative, yung formula no, natin, kung ang susundin natin yung unang given na arrangement, compared sa kung ang susundin natin ay yung bagong arrangement natin na diagonally dominant. Magkaiba yung form ng iterative formula natin nun. Okay? So, we will base our iterative formula dun sa bagong na rearrange na system. So, our iterative formula will be for x1, no? So, again, that will be ang equations natin ay 5x1 minus 2x2 plus 3x3 is equal to negative 1. So, mula dito, okay, we will solve for x1. So that's x1 is equal to negative 1 plus 2x2 minus 3x3 all over 5 or multiplied by 1 over 5. And then, yung second equation natin is negative 3x1 plus 9x2 plus x3 is equal to 2. So, ang ating formula dito, we solve na for x2 from the second equation. That will be 2 plus 3x1 minus x3 all over 9 or times 1 over 9. And then, yung third equation natin, so na-rearrange natin na form, no? 2x1 minus x2 minus 7x3 is equal to 3. So, we solve for x3 from the third equation. So, that will be 3 plus or minus 2x1 plus x2 multiplied by negative 1 over 7 or divided by negative 7. Okay. So, this one will be, this 3 will be our formulas, okay, in solving for the refined estimates of your x1, x2, and x3. Remember, ang solution natin is x1, x2, x3, no? Collective siya, no? Hindi lang x1, hindi lang x2, hindi lang x3, kundi yung buo. Kaya yung tatlo na yan. Kaya lahat sila will be part of the solution to your given system. Okay. So, yung ating gagawing initial guess, since wala namang specified na initial guess tayo, ang gagamitin natin ay 0, 0, 0 as our initial values of x1, x2, and x3. So, x1 initial, that's 0. x2 initial, that's also 0. And x3 initial will also be 0. And again, our stopping criterion is you should have a relative error of less than or equal to 10%. So, unahin muna natin yung Jacobi method. So, as you can see, yung preliminaries natin na ginagawa sa solution natin, meaning yung pag-check ng row sum criterion, kung diagonally dominant yung system, at saka yung pagta-transform ng ating diagonally dominant na system sa papunta sa ating iterative formulas, no? Pag-solve ng unknowns dun sa equations, no? Yan ay for both Jacobi and Gauss Seidel, ganyan ang ginagawa. Okay? Kaya yung ating starting point dito sa Jacobi method at mamaya kapag ginawa natin yung Gauss Seidel method, we will start with the same. Okay? Ang same initial guess, we will use the same iterative formulas. Okay? Meron lang pagkakaiba kung paano natin pinaperform yung mismong iteration. So, for the first iteration of Jacobi method, we will be solving for the value of the refined estimate for x1 using our iterative formula, no? To be 1 over 5 times negative 1 plus 2 times ang x2 natin initially ay 0 minus 3 times ang x3 natin 0. And then si x2, we will solve as 1 over 9 times 2 plus 3 times 0 minus 0. And then si x3 will be negative 1 over 7 times 3 minus 2 times 0 plus 0. So basically, ginamit lang natin lahat ng given na initial estimates natin for x1, x2, x3 and substitute doon sa ating iterative formulas. x1, x2, x3 doon sa iterative formulas natin. So with this, we will be getting values equivalent to negative 0.2, negative 0.222, and negative 0.42857. Okay. So, wala pa tayong isosolve dito na relative error kasi puro 0 lang naman yung pinanggalingan natin. Pag sinolve natin yan, 100% lang naman na makukuha natin na error dyan. So, we will be solving our relative error after the next iteration. So, this one is only our first iteration. Iteration 1. So, for iteration 2, ang gagawin natin ngayon, itong lahat na to na nakuha natin from the first iteration, yan ngayon yung magiging next na pang-substitute natin sa second iteration. So, if you may recall, dun sa fixed point iteration natin, method, no? First fixed point iteration method last time, ganun ang ginagawa natin. Carry over lahat siya. Okay? Kaya siya tinawag na total steps, no? So, tapusin mo muna lahat, x1, x2, x3, lahat na makukuha mong values ay gagamitin mo para doon sa x1, x2, x3 for the next iteration. Okay? So, for the second iteration, iteration 2, we will be having your x1 to be equal to, so same formula ang gagamitin mo, no? Ito pa rin. x1, x2, x3. Same iterative formulas pa din. Pero yung values ng x1, x2, x3 na gagamitin mo dito is kung ano na ngayon yung nakuha natin from our iteration 1. So, we have your x1 to be 1 over 5 multiplied by negative 1 plus 2 times. So, from the previous iteration, ito yung value ni x2 and then minus 3 times negative 0.42857. And then for x2, we will have 1 over 9, 2 plus 3 times negative 0.2. Ito yung value ng x1 from our first iteration. And then minus x3 from our first iteration, negative 0.42857. Then x3 is equal to negative 1 over 7 times 3 minus 2 times x1 from the previous iteration, 0.2. And then, plus x2 mula sa iteration 1.222. So, we'll have here values of 0.14603, negative 0.20317, and negative 0.51746. Okay? So, lahat ng x1, lahat ng x2 and x3 na nilagay natin doon sa same iterative formulas ay nanggaling lang from the first iteration. So, we can now solve for the relative error. Pag nag-solve tayo ng relative error, that will be with respect to each of the unknowns. So, kung tatlong unknowns tayo, meron tayong relative error with respect to x1, x2, and x3. So, relative error sa x1, pero ganun pa rin, no? Present minus previous over present estimate. 0.14603 minus negative 0.2 over 0.14603 times 100. So, we have here 236.95%. So, huwag kayong ma-alarm kung ganyan kalaki siya sa simula. Talagang at the start, normal na merong mga ganyan na values na malaki yung relative error sa simula. Pero remember, this one, dahil na satisfy natin yung rule sum criterion, then sure tayo na later on magko-converge ito. Okay? So, sa simula lang siya malaki na ganyan. No? Next, for x2, ang relative error natin ay 0.20317 minus 0.222 over 0.20317. Times 100, we have 7.37%. So ayan, medyo mas maliit ngayon, no? Mas hamak liit nung ating error sa x2. Okay, so mas malapit sila, no, sa bawat isa, yung previous and present estimate natin. And then sa third unknown, x3, ang relative error natin ay negative 0.51746 minus negative 0.42857 all over negative 0.51746 times 100. So you have 17.18%. Okay, so dito, remember, no, kapag nag-satisfy ka ng relative error, kailangan lahat sila ay masatisfy yon. So kung ang isa, halimbawa, yung x2, na-satisfy na yun yung less than 10%. Si x3 at saka si x1, hindi pa. So ang ibig bang sabihin, mag-stop ka na sa x2. Ang i-iterate mo na lang sa next iteration, iteration 3 ay x1 at x3. Hindi ganon. Okay? So, hanggat hindi sila lahat nag-less than 10%, tuloy ka pa rin ng iteration. So, ibig sabihin, yung 0.2037 natin for x2 sa iteration 2, although 7.37% lang yung error niyan, isa-subject pa rin natin siya sa next iteration. So, mababago pa yan. Okay? Hanggat hindi sila lahat nagle-less than 10%. So, sa next iteration, iteration 3, lahat ng values sa iteration 2, carry over papunta sa iteration 3. We will use the same set of formulas. Okay? So, you have here 1 over 5. So, I'll be using the same formula, no? So, for x1, yung 1 over 5, negative 1 plus and so on, and so forth. Sa x2, ganun din. Sa x3, ganun din. So, we will be having the values for the third iteration. No? Hindi ko na isa-isahin, no? Hopefully, nakuha nyo naman na yung process. So, for x1, you will be getting 0.919191174. For x2, we will be getting 0.3283 839. And then for x3, we get negative 0.41587. So those are the values after a third iteration ng Jacobi method. And then the relative errors, okay, for x1, we will be getting 23.84%. For x2, we will be getting 37.56%. And then for x3, you have 24.43%. So you see, tumaas yung error natin sa x2, pero bumaba na yung error sa x1. So again, goal natin, mapababa sila lahat ng less than 10%. So next iteration natin, so sa iteration 4, again, carry over pa rin lahat ng values ng x1, x2, x3 from the third iteration. Ipa-plug in lang natin siya ulit sa iterative formulas natin, okay, na arrive kanina. So, we will have the values of x1, okay, for the fourth iteration, no? A value of x1, 0.18088. x2, you have 0.33234. And then for x3, we have negative 0.42070. Now, solving for the relative error for x1, we will get 6%. For x2, we will get 1.19%. And for x3, the error is 1.15%. So in this case, all of this are already less than 10%. Okay? So therefore, we now stop iteration and conclude now that, okay, hence, the solution now, x1, x2, x3, will be approximately equal to what we obtained here, 0.18088, 0.33234, and negative 0.42070 using the Jacobi method. Now, for the Gauss Seidel method, so again, hindi tayo magta-transform ng panibago ha. Dahil same problem lang naman to, same system, yun pa rin yung magiging iterative formula natin. Okay? Tapos, we will start with our initial guess. Ganun pa rin, 0, 0, and then for x3, 0 din ang initial natin. Now, for the first iteration of Gauss Seidel method, okay, si x1, okay, ganun pa din yung formula. 1 over 5 multiplied by negative 1 plus 2 times x2, okay, that's 0, minus 3 times x3. So, you'll get negative 0.2. Same dun sa kanina sa Gauss Seidel, no? For the first iteration, value ni x1. Same sila. Now, dito ngayon yung kakaiba ngayon sa Gauss Seidel sa Jacobi. Kanina sa Jacobi, nakikita natin na kapag sinet up natin yung ating x1, x2, x3 sa iterations natin, pwedeng, before natin i-compute, pwede natin i-set up na agad yung yung values, di ba? Pwede natin i-plug, i-substitute na agad lahat, and then tsaka natin i-compute siya isa-isa. Okay? Sa Jacobi method. Kasi nga, total steps, lahat ng values from the previous iteration, pinapasok natin, okay, doon sa next iteration. Dito sa Gauss Seidel, yun yung nagkakaiba. Iteration by single steps. After mo masolve sa x1, pag kailangan mo siya ngayon sa value ni x2, okay, ilalagay mo na agad yung value ng x1 na previously mo nakuha. Okay? So, dito, x2, which is 1 over 9 times 2 plus 3 times x1, yung x1 na ilalagay mo na dito, hindi na 0. Kasi meron ka ng x1 from our refined estimate of x1, no? Okay? So, ito na mismo yung ilalagay mo. Okay? And then, plus x3. Kaso si x3, wala pa naman tayong bagong value. So, 0 lang ilalagay mo dyan. Which is equal to 0.15556. And then, for x3, so, same iterative formula, negative 1 over 7 times 3 minus 2 times x1. So, ilalagay mo na si negative 0.2. And then, plus x2. So, si x2, ang ilalagay mo na dito, si 0.15556. Hindi na 0. Kasi, meron ka ng previously na nakuha na value ni x2. So, this one will be equal to negative 0.50794. So, yan ngayon yung ating refined estimates ng solution natin after the first iteration of Gauss Seidel method. So, yan ngayon yung pagkakaiba, no, ng Jacobi sa Gauss Seidel in terms of how you apply or you use, no, yung previous values na nakuha natin doon sa ating iteration. Okay? So, sa Gauss Seidel, we are already using the refined values within the iteration itself. Kaya hindi ka pwedeng makaka-proceed sa pag-solve ng x2 hanggang hindi mo pa nasa-solve muna yung value na refined ni x1. Kasi gagamitin mo na agad siya. Kasi hindi ka makapag-proceed sa pag-solve ng value ng x3 kung hindi mo pa nasa-solve yung actual na refined value ng x2 within that iteration. Kasi gagamitin mo na siya to solve for x3. Okay? So, for the next iteration, hindi mo natin isosolve yung ating percent error dahil again, 100% pa naman na error yung meron tayo after the first iteration if it's only relative to your 0, 0, 0 initial guess. So, iteration 2 na tayo. Sa iteration 2, again, same set of formulas. Okay? x1 will be equal to 1 over 5 times, okay, you'll have negative 1 plus 2 times x2. Ang x2 na gagamitin mo, yung 0.15556, yung nasa previous. Okay? And then minus 3 times x3, negative 0.50794. So we get 0.16669. And then for x2, sa second iteration natin, 1 over 9 times 2 plus 3 times your x1. So, gamitin mo na si 0.16669. And then, minus x3. So, si x3, yung ating value doon sa iteration 1, negative 0.50794. This gives you 0.33432. And then, for x3, that will be negative 1 over 7 times 3 minus 2 times x1, so 0.16669, plus x2. So, gagamitin na natin si 0.33432, which gives us negative 0.42862. So, makakapag-solve na tayo ngayon ng ating relative error. Okay, after the second iteration, percent error sa x1, you get 0.16669 minus negative 0.2 all over 0.16669 times 100, so that's around 219%. So again, malaki na naman to, no, ng error natin. Kasi yung isa positive, isa negative value, no? Anyway, but that's just the first iteration. For x2, you have 0.33432 minus 0.15556 all over 0.33432. That's an error of 57.47%. And then for x3, you have absolute value of negative 0.42862 minus negative 0.50794 all over negative 0.42862 times 100, so you get 18.56% error. So again, our target is less than or equal to 10%. Okay? So dun sa next iterations natin, ganun ulit yung gagawin natin, no? So same formula, same iterative formulas. We solve for x1 using the values sa previous iteration natin, pero dun sa x2, dun sa x3, ang gagamitin na natin is kung ano yung nakuha natin within the iteration. So, when you apply Gauss Seidel kay iteration 3, we will be getting values of x1, x2, and x3 to be 0.19090. For x2, that's 0.33348. x3, you will get negative 0.42167 with relative errors of, for x1, we have 12.52%. For x2, that will be 0.25%. And then for x3, we get 1.65%. So, you see, dito, mas mabilis mag-converge, no? Compared dun sa Jacobi. Dahil after the third iteration, nasa 0.25, 1.65% na lang. Tapos 12.52% na lang yung ating error sa x1. Okay? Na hindi natin nakuha yung ganito kaliit kahit anong pagdating natin sa fourth iteration doon sa Jacobi method. No? It's because sa Gauss Seidel nga, nagagamit mo na agad yung ating refined estimate within the iteration itself. Kaya we expect na mas madali siyang magko-converge. Pero dito, although 0.25, 1.65 na si x2, x3, yung error nila, no, si x1 greater than 10% pa rin. Kaya, hindi pa tayo mag-stop ng iteration dito. Okay? So, we still need one more iteration, iteration 4. Sa iteration 4, ang makukuha nating value, no, I'll leave this to you as an exercise na try nyo i-verify. 0.18639, x2 is 0.33120, and x3 is negative 0.42263. And when you solve now for the relative error for x1, that will be 2.43%. Relative error for x2, that will be 0.69%. And relative error for x3 will be 0.23%. So, lahat na to already less than 10%, which is our prescribed stopping criterion. Hence, okay, our solution, okay, x1, x2, x3 will be approximately 0.18639, 0.33120, and negative 0.42263.